In this and the next couple of videos, we're going to be talking about singular value decomposition because it has wide applicability, because it can be applied to any matrix and it has a number of very useful and powerful applications. Essentially, it allows us to extend the ideas of eigenvalues, eigenvectors, diagonalization, eigendecomposition, all these things that we've found so useful so far in this chapter, but we can extend those ideas to any matrix, rectangular matrices, even complex matrices, as we'll see in a later video. We'll focus on real matrices for now, but it also applies to complex matrices as well. And because it applies to any matrix, we can use it as a diagnostic tool, similar to the determinant in chapter 1. And it also has many important applications throughout science and engineering that we'll also emphasize as well. So let's discuss the framework first. I want to kind of motivate the idea behind it, which again is this notion that we can extend eigenvalue, eigenvector, diagonalization concepts to non-square matrices. Obviously, they only exist for square matrices, so we want to extend those same ideas in some way to apply to any matrix. So that's our motivation. Well, we'll get to the applications in a later video. And so let's kind of use that motivation to walk through a framework that leads to what the SVD, singular value decomposition, is. And I'm going to start by giving a wish list. So these are things based on our discussions thus far that we've been learning throughout this chapter. And so if I could be so bold as to ask for just a couple things. So the first would be, we would like an eigen-like decomposition, but we'd like it to apply for any matrix A. Remember in the previous video, we had 3 different eigen decompositions depending on the nature of A and its eigenvalues. Wouldn't it be nice to have a single decomposition that applies to just any matrix, no limitations? Again, including rectangular matrices. Wouldn't it be nice if we always ended up with diagonal matrices and orthogonal matrices? So all the vectors that form the modal matrix are orthonormal. So that might seem too much to ask, to have those properties that apply to any matrix A. But as we'll see, if we focus on the first one of these, we'll actually get the second for free. So let's take a look at how this works out. So obviously, once again, eigenvalues, eigenvectors, diagonalization, eigendecomposition, they only apply to square matrix A. So in order to extend these ideas, we have to not use A, but use something else that involves A. Now, if you remember back to section 2.4, we were talking about normal matrices. And in the process of doing so, we discussed these matrix products, A transpose and A transpose A. So A here is any matrix A of size m by n. For now, we'll assume that A is real, but otherwise it's any matrix m by n. And I'm just going to highlight some of those properties that we came across. So both of these matrix products, A transpose A, they both produce a square product. So the product is always square. A transpose is m by m, and A transpose A is n by n. So they're different sizes in general, if m and n are different, but they are square. More importantly, they are always symmetric. So regardless of the A matrix, as long as it's real, doesn't matter size and shape, if you take A transpose or A transpose A, the result will be symmetric, and we showed that in section 2.4. We also mentioned that the 2 matrix products have the same non-zero eigenvalues, and all the rest of the eigenvalues are 0. They're positive semi-definite, so all the eigenvalues are non-negative. And then finally, from the fact that these matrix products produce symmetric matrices, we can then conclude that the eigenvectors of both are mutually orthogonal, or at least can be made to be mutually orthogonal. And so that's what's going to give us that second of my wish list items. Now, of course, you're thinking we're talking about something completely different. So A and A transpose A, they come from A, but they're not A. So where is this going? Well, let's just kind of follow through with this logic and see where it leads us. So I have these wonderful properties of A transpose and A transpose A. Let's see if that can somehow circle back and give us a useful decomposition for A itself. So let's just start by forming the eigenproblems for these 2 matrix products. So for A transpose, we'll use sigma squared. I'll discuss why it's squared in a moment. sigma squared as the eigenvalues, and u as the eigenvectors. And similarly for A transpose A, we'll have sigma squared as the eigenvalues and v as the eigenvectors. You'll notice, of course, that we're building in here the fact that the non-zero eigenvectors are the same in both of these problems. Okay, so we have two eigenproblems for A transpose and A transpose A. U and v are the eigenvectors, respectively, of those two matrix products. So let's start by thinking about the eigendecompositions for these two matrix products. So AA transpose, we know can be written as a matrix, we'll call it U, times a diagonal matrix. For now I'm going to call it sigma sigma transpose, you'll see why in a moment, times U transpose. Remembering that AA transpose is symmetric, this is like the Q times D times Q transpose eigendecomposition we had for real symmetric A with distinct eigenvalues. Now these two modal matrices U and V, as you might guess, they will contain as their columns the orthonormal eigenvectors little u and little v of these two matrix products. So the eigenvectors of A transpose are the little u's, they comprise the columns of capital U, and then the eigenvectors V of A transpose A form the columns of the modal matrix V. Remembering that these are now different sizes. Now let's look at the sigma. So the sigma is an m by n matrix, so it's the same size as the original A matrix, and it is diagonal, so it only has non-zero elements down the main diagonal. And those elements are going to be the sigmas. So remember, the sigma squareds are the eigenvalues of A transpose and A transpose A. And then the square roots of those, it's actually going to turn out to be the positive square roots. We'll discuss that in a little bit. The square roots of those, the sigmas, are going to be sitting on the diagonal. We call those the singular values of the matrix. Again, we'll get to that in a little bit. So given that, when you take sigma times sigma transpose, that's going to be a square m by m matrix with the sigma squareds, again the eigenvalues, along its diagonal. Similarly, sigma transpose sigma is going to be now an n by n matrix with those same non-zero eigenvalues along its diagonal. So in that way, we have our D. So there's two Ds, they're different sizes depending on the m and n dimensions of the original matrix A. But in any case, in both situations, we have our usual eigendecomposition, an orthogonal modal matrix times a diagonal matrix times the transpose of that modal matrix, both here and here. They are different modal matrices because they are comprised of the eigenvectors of these two different matrix products. All right, so all we've done so far is show that we can indeed construct this eigendecomposition for these matrix products. Again, that doesn't circle us all the way back to getting a decomposition of A, but we're getting there. Just give me a couple more slides. So we need to see how this provides a diagonalization approach for the matrix A itself. So let's take a look at these again. I'll take the left one first and the right one second. So let's take this one and see how we can manipulate it to expose this SVD. So here it is repeated. A transpose is U sigma sigma transpose U transpose. Now what I'm going to do is I'm going to insert V transpose V, which of course is just the identity matrix because V is an orthogonal matrix, so V transpose is the same as V inverse. So V inverse V is I, the identity matrix, so it's like multiplying by 1. I'm going to insert that into the middle of this product of matrices. So I have my V transpose V here. Again, that doesn't change anything because that product itself is equal to the identity matrix I of the appropriate size. Now I'm just going to regroup these matrices. So I have U sigma V transpose times V sigma transpose U transpose. Finally, I'm going to take the second one here in parentheses and I'm going to rewrite it in terms of the transpose. And remember, the transpose of the product of matrices is the product of the transposes in reverse order. So if you'd like, look at this backwards. So we have V transpose transpose, which is just V, so that's here. We have sigma transpose, and then we have U transpose. And you'll notice the reason why I've done this is now the things in parentheses are both the same, and they correspond to A and A transpose. Here's A, and here's A transpose. So it looks like I can write A as U sigma V transpose, and indeed I can, and that'll be the SVD. Now let's do the other one just to be sure that that works out the same. So let's take the A transpose A is equal to V sigma V transpose, the second of those two relationships. And let's do a similar thing. Let's take U transpose U, which of course is equal to I for the same reasons as V transpose V is equal to I. Insert that in here. Regroup our matrix products such that I now have V sigma transpose U transpose times U sigma V transpose. Now it's this one that I want to rewrite in terms of its transpose. So again, let's look backwards. So I have the transpose of U sigma V transpose. If I take the transpose of V, of course I just get V back, sigma transpose, and U transpose. And so once again, I have A is U sigma V transpose, A is U sigma V transpose. So what this is showing is I can write my A matrix, my original rectangular A matrix, as the product of these matrices U, which remember is orthogonal, sigma, which is diagonal but of the same size as the original A, times V transpose. So that is the singular value decomposition. I've repeated it here. So this is the final result. A can be written as the product of U, sigma, and V transpose. Sigma here is an M by N diagonal matrix, again the same size as A. U is an M by M orthogonal matrix corresponding to A transpose. And V is an N by N orthogonal matrix corresponding to A transpose A. So once again, the capital U is the modal matrix that has the eigenvectors, which are the little u's, which are the orthonormal eigenvectors of A transpose. Then capital V, which is the modal matrix for A transpose A, that has its columns, the little v's, which are the orthonormal eigenvectors of A transpose times A. So we can see a lot of similarities for our previous diagonalization procedure for real symmetric matrix with distinct eigenvalues. However, this now applies to any matrix A, but in order to do so, we actually need two modal matrices rather than just one. And you can see that from the size M by N of A that we would need different modal matrices to get the sizes right. Once again, this applies to any real matrix as it's written here. It can be done for complex matrices as well. Again, what we have essentially is a generalization of the eigen decomposition of square matrices now applied to any matrix. We've mentioned that the non-zero eigenvalues of A transpose and A transpose A are the same. What about the eigenvectors? So they're the little u's and the little v's, but are they in any way related? And it turns out that they are. So let's show that. So let's start with the SVD itself. A is U sigma V transpose. And let's rewrite that by post-multiplying V on both sides in the following form. A times V is equal to U times sigma. Similarly, we could take the transpose of our SVD and post-multiply U on both sides, and that gives us this. A transpose U is equal to V sigma transpose. So if I take this first one, where here obviously it's written in matrix form, if I write out the U's and the V's, the columns of capital U and capital V, I can see that I have this relationship. So A times V is sigma times U. So of course the normal eigenrelationship is A times U is lambda times U. What we see here is now when I take A times V, rather than getting back the original V vector, I get its corresponding U vector. And of course the eigenvalue is the singular value sigma. Similarly, from the second relationship, I get that A transpose U is sigma V. So if I take A transpose times one of the eigenvectors U, I'm not going to get back U. Instead, I'm going to get back the corresponding V with the same sigma. So these relationships are very important, will form the basis for part of the algorithm which we use to get the SVD. So just some terminology here. You've already heard me refer to the sigmas as the singular values. So they're related to the eigenvalues. They're not the eigenvalues of A transpose A or A transpose, but they're related to them. And then the U vectors are called the left singular vectors. So remember, they're the eigenvectors of A times A transpose. We call those the left singular vectors. Left because U is on the left, and then the V's are the right singular vectors because V is on the right. So then the V vectors, which again are the eigenvectors of A transpose times A, those we call the right singular vectors. So again, they're not eigenvectors of A. There are no such things if A is not square. They are the right singular vectors. Once again, they are related in this very special way that we've just shown here. So we'll take advantage of that in the method that we'll use to actually get this SVD of a matrix. So let me just close by kind of circling back to our wish list. So as advertised, or as we wished, the SVD applies to any matrix. It allows us to extend the ideas of eigenvalues, eigenvectors, diagonalization, and so forth to now any matrix, not just square matrices. And it's based on the fact that A transpose and A transpose A are both square and symmetric for any real A. In terms of the graphical interpretation of this, I kind of hinted at it in the previous slide. So the regular eigen problem, where we have A, U is lambda U, the U vectors are special vectors that correspond to a matrix A, such that when you take A times U, that transformation gives you back the same U vector, and it just gets longer or shorter based on the size of lambda. Here, it's a little different. So the U's and the V's are still special vectors related to A. They're the left and right singular vectors. But rather than behaving like eigenvectors, they behave in the following way. So now when I take the matrix A times, for example, a U vector, I don't get back the same U vector. I get a V vector that's been stretched by the singular value. So again, they are related geometrically and mathematically, the U's and the V's, but they are not, of course, the same. And what we're going to see in the coming videos is that SVD itself, while I'm posing it as this generalization, the applications are going to go well beyond just being able to do a diagonalization type operation in more general context. There's going to be a lot of applications that we'll mention, some of which we'll use as examples.